Hi, everyone. We're going to start part 2. So we have Muhammad Reza Khalin. He's a postdoctoral researcher in the statistics department at Columbia. Previously, he earned his PhD in electrical engineering from USC, as well as an MA in applied mathematics. His research focuses on statistical learning theory with a particular interest in transfer learning and domain adaptation. Specifically, he studies methods for transferring knowledge and information from tasks with abundant data to those with limited data.
Hello, everyone. I'm very happy to be here to talk about my research on transfer learning in Outlier.
Sorry to interrupt you. Can you press the button on the screen?
Oh, yeah. Okay. Hello, everyone. I'm happy to be here to talk about, I think, to talk about my research. Sorry. My research on transfer learning in outlier detection. This is joint work with Samori Potufe from Statistics Department. Yeah, so the problem of outlier detection happens in many scenarios, like in climate applications. For example, we are interested in detecting rare events like heavy rain or wildfire detection. So in these problems, we have two classes. From one class is very common, but the other one is very rare and it's not likely to happen. And we are interested to detect the rare event. And you see, we have two types of errors. One type of error is that, for example, we have heavy rain, but we fail to detect. But the other type of the error is that we do not have a heavy rain, but we flag like a heavy rain. And you see that these types of errors are very different. So if I want to compare the traditional balanced classification with outlier detection, or you can call imbalanced classification. In traditional classification, in both of them, we have two classes. But in traditional one, we have enough number of samples from both classes. But in the outlier detection, from one class, we have abundant of data. But from the other one, we have a few data. And sometimes we do not have any data. So the challenge is that in traditional classification, balanced classification, we can just minimize the total loss or total error if the number of the samples from two classes are kind of the same. But if we do it in the outlier detection in the imbalanced classification setting, if we minimize the total loss, we can find a function, we can find a classifier that achieves a low error on the total loss. However, the error with respect to the class from which we have a few data could be very high. And it's not good because we want to have a classifier achieves low error on both classes. So there are some popular approaches to this problem. One of them is called cost-sensitive learning in the literature. So what people do is they minimize weighted loss. So they assign a C, a weight to one of the loss and one minus C to the other loss. There's a challenge in this approach. How should we assign this C? Because it requires a priori class probabilities, and we have a few samples from one of the classes, and we cannot estimate the a priori class probabilities. The other approach, less studied in the literature, is called Neyman Pearson classification. It's related to the also hypothesis testing problem. So in this setting, we have two types of errors. We want to minimize one type of the error subject to the constraint that the other type of the error is less than alpha. And here the objective one is called type 2 error, and the constraint is called type 1 error. And this alpha is a user-specified threshold. For example, if I want to give you an example, For example, the rain detection problem. One trivial classifier is that always you can say that, oh, today we are gonna have heavy rain. So if we do that, the objective loss is 0, but the type 1 error is huge, and that also reflects the cost. For example, if you say that we are going to have we are going to have a heavy rain today, then we have to take some emergency measures. If we were wrong, then we have to pay some cost. So that alpha reflects the cost in most of the applications. Also in this example, so in this framework, first of all, there's an asymmetry between errors. One type of the error is much more important than the other type of the error. So see that in the wildfire detection, a type 2 error is that the wildfire occurs, but we fail to detect. The other one is that wildfire does not occur, but we flag a wildfire. So again, this problem has been studied a lot in the statistics literature when we have access to the underlying distributions. So there's a famous lemma, it's called Neyman Pearson lemma. It characterizes the optimal solution of this problem when we know the probability distribution of the two classes. And the optimal solution is simple. If you have distributions, then if you plot the density ratios of one class to the other class, then you just need to find a threshold. Then the optimal function, optimal classifier has the following form. If the density ratio is larger than some threshold, you say it's class 1. If it's less than a threshold, then it's the other class. But the challenge is that we only have some samples, specifically from the outlier class. We have a few data, and it's not possible to estimate the probability densities. So the problem becomes challenging when there's a scarcity of data in the outlier class. Now, one approach to mitigate this challenge is using transfer learning technique. So this is our problem. We also call it target. This is our goal. We have two classes, class 0, class 1. From one class, we have many data. From the other class, we have a few data. It's challenging to find a good classifier. So the challenge is the scarcity of the outlier data. So one natural approach is to get help from some other related data sets. So we can call it source. So in the source also, it's another outlier detection problem. However, from the other class, we have from class 1, we have more data. And we also assume that the class 0, which we can call normal distributions, are the same in target and source, but the distribution of the outlier classes could be related, also could be different from each other. And the problem is that how can we get help from the source in order to improve the accuracy in the target problem? Also, let me give you a concrete example in the climate data. Let's say target is one location. In a specific location, we want to detect heavy rain, but we do not have data from that specific location. But source could be other locations, but from some other locations, we have enough data. And it's fair to assume that the normal distribution of the rain, not heavy rain, is kind of the same between two locations, but the distribution of the heavy rain could be different from one location to other location. So it depends how you define the source and target. Source and target could be two different locations, could be time. For example, target could be the current year, source could be the past years. From past years, you have gathered many data. From, for example, in the current year, you do not have enough data. So there are some questions here. How should we leverage source samples to improve accuracy in the target task? Can we just combine them naively, or we should combine them in an effective way? So that's one question. What if the second question is very important. What if the source distribution is unrelated to the target? So sometimes, because we have some samples, we do not know the distributions. We cannot also estimate the distributions because we have a few samples. Sometimes the distributions could be very different from each other. Then the phenomenon of negative transfer happens. So negative transfer, it means that it's better not to use source because sometimes it can mislead you. And the third question is that do we need to have a prior knowledge of the relatedness between source and target distributions? Do we need first to know that source and target are related to each other, then perform transfer learning, or we can come up with an approach automatically detects when we should use a source, when we should avoid or ignore source. So here we are proposing a meta procedure. It's a very generic procedure, and in the later we are going to implement this procedure. So this is a constraint optimization problem. It has an objective function and two constraints. So let's understand line by line. So the last line, which is one of the constraints, ensures that the type 1 error of the function we want to obtain is below the pre-specified threshold. So here, this line filters out the functions whose type 1 error is large. Then the second line, first of all, this h hat on the right-hand side is the function obtained using only target. So first you ignore the source, you do classification, you find the function from the target. So that's h hat t. The second line retains functions whose performance is close to this the function obtained on the target plus additional term. So if you consider that additional term, if the number of target samples is large, then h hat t is reliable because it has trained on enough number of samples. So h hat t is good. So that term goes down. So we only retain the functions that are very close to that h hat t. But when the number of target sample is low, meaning that h hat t has been trained on a few number of target samples. So it's not reliable. So we have to retain more functions. So that ensures that our function would not very far from the function trained on the target. And then on this class of functions, we are minimizing the source, we are utilizing the source data, and we are minimizing the type 2 error on the source data, which utilizes the source samples. So you see that this approach guarantees that we will never have negative transfer because we are minimizing source error on the functions that are close to the function trained on the target. So first, we derive the theoretical guarantee for this approach. So that procedure is on training data, but we have to make sure that if when we get a function, how is its performance on the test data or generalization error. So we prove this. First of all, it guarantees that on the test data, the type 1 error on the target in the target domain is less than alpha, and type 2 error is less than minimum of 2 terms. So let me explain that 2 terms. It consists of 2 terms. One of them depends on so that one is the number of target samples, and the other one number of the source samples. So if you pay attention to the second term, first of all, it ensures that source does not hurt you. At least you can get the rate can be obtained by using only target samples. And then the other term is that if source is helpful, if source is informative about the target, you can leverage the information from the source. There are also some other parameters here. So that row, I'm not going into the details of these parameters. It kind of captures the transfer distance. It captures the value of source samples. If rho is a small, like if rho is 1, then source sample is more valuable. If rho is large, like 10, 20, then the source samples are less valuable. So it captures the distance between source and target. Also, that delta is the let's say you have obtained a function using only source, and then you evaluate that function obtained on the source on the target. So that delta is the target error of the best source function in the target domain. So that's the theoretical guarantee. Next, we want to implement this procedure. So let me use these notations. R phi P0 is the risk of H on normal distribution. We call it P0. That phi, it reflects the loss function we are using. Could be logistic loss, exponential loss. And then we have a target type 2 error. Sorry, it should be source type 2 error, is PS. And the other one is target type 2 error. So this procedure is a optimization, a constant optimization procedure. So we are using Lagrangian. If you write down the Lagrangian, it will have this format. So here, two tuning parameters appear. Lambda S is the tuning parameter for the source risk, and lambda T is the tuning parameter for the target risk. So we are not doing brute force search. We have developed a smart way how to find these tuning parameters. So first you fix lambda S, and you find you've changed the lambda T so that in order to get some functions whose type 1 error is close to the alpha. So for each pair of lambda S, lambda 0, you have to train it, and you get a function. So using this smart way, you get a bunch of functions. So the initial class of functions, for example, let's say it's a class of neural networks, can be reduced to H hat. So all the functions in the H hat satisfy the type 1 error constraint. And then it requires another filtration step. So you use target samples to filter some of these functions, and in order to get another reduced hypothesis class or class of functions. Again, also that depends on the number of the target samples. If the number of target samples is low, then you retain more functions. If the number of target samples is large, then you retain fewer functions. Finally, you use the source samples, you minimize the source error on this reduced class of functions. So properties of this proposed algorithm is that, first of all, it does not require prior knowledge about relatedness between source and target. You know, we can have source and target that are very close to each other, their distribution, and we can have source and target that are very far from each other. And so if the source contains information relevant to target, we will, on the experiments also, you will see that the algorithm leverages the information. If the source is irrelevant to the target, the algorithm avoids negative transfer. So automatically, if source is useful, it exploits source. If source is not useful, it avoids source. And also the algorithm is model-free, meaning that you can consider class of neural networks, kernel machines. We do not have any assumption on the architecture of the neural network, like could be CNN, etc. So here we have conducted some experiments on climate data. So we are using the dataset ClimSim, large multi-scale dataset for hybrid physics ML climate emulation. So in this dataset, from each location, we have some data. Depends on longitude and latitude of the location. So we have merged some neighboring locations, and we have created some clusters. So the data has 124 numerical features like temperature, humidity, etc. And it has many outputs. So we have extracted only the output of the rain. The original problem is a regression problem. So we used the 95th percentile to create a binary problem. So one class is heavy rain, the other class is non-heavy rain. We want to predict the heavy rain using these input features. So here is the result. We have implemented our algorithm and some other approaches existing in the literature. So here, type 1 error, which is alpha, is 5%. And we are measuring the test target type 2 error. And here we are increasing the number of the source samples from 100 to 2000. Number of target outlier you see is 25. The other class 3000. It's heavily imbalanced. First, look at these two plots on the top. So one common approach in the literature is that you do a classification, you find a function, they call it a score function. But for example, you get a score function, and in traditional classification, if the score is above half, you classify to one class. If it's less than half, you classify to the other class. Then you can change that threshold in order to satisfy the type 1 error. So you get a score function, and by changing the threshold, you can satisfy the constraint on the type 1 error. So if you do that, the dashed line is just using only target thresholding approach. You see that's very large. And this one is pooled source and target. You just combine source and target data, and then you use that thresholding method. So you see that it's not good. These methods, all of them are Neyman Pearson approach based on our implementation. And I'm comparing, the black one is the full version of the Neyman Pearson, and I'm comparing with the other variants. For example, the blue one is that you just use target, and the other is that you just use source. And the other one is that you just naively combine source and target, and you run the algorithm. But the black one is not naively combine source and target. It effectively combines source and target. So first of all, you see that we have, for example, gain with respect to the baseline of only target. It shows that source is helpful. We can reduce the target error using the source. However, you see that the only source or just pooled source and target also, they work well when we have more samples. So they're kind of close to each other. So you may ask us, so why you should use this a little bit complicated way to combine source and target? We can just combine them naively and run the algorithm. The problem is that we don't know source is close or far. So here you see that in the previous one, source is informative. So because source is good, source is close to the target, only source method or pooled source and target perform well. But when source is not good, they suffer from negative transfer. So we ensure that our approach is close to the only target approach, meaning that source is not helpful, and we want to just ignore the source so we can be close to the baseline. But the other approaches suffer from negative transfer because they're just naively combine source and target, and they're not adaptive to the data, meaning that they cannot detect whether source is helpful or is not helpful. So that's the message of the algorithm, is that it's adaptive. If source is helpful, it exploits. If source is not helpful, automatically ignores the source. So if I want to summarize the talk, we propose the meta algorithm as a constraint optimization procedure with a theoretical guarantee on the generalization error. We implemented an instantiation of that meta procedure using Lagrangian method. There could be another instantiations of the procedure. We conducted some experiments. The experiments show that the algorithm utilizes source when source is related and avoids negative transfer when the source is not related. Also, we submitted this work to AI Stats 2025, transfer Neyman Pearson algorithm for outlier detection. The reviews were positive. The reviews were positive. I think it will be appear on AI Stats. Also, we have conducted additional experiments in the paper, not just climate data. The approach is very generic. It could be applied to financial data, to climate data, etc. Thank you. Any question?
Hi, very interesting talk. I'm wondering, when you were showing, maybe I'll just ask the transfer distance row value.
Oh, yeah.
So in order to do this proof, do you have to like be able to define that analytically? Could you maybe explain?
Yeah, a good question. It's a very, I mean, people have defined different notion of transfer, how to quantify the notion of transfer between source and target. This row reflects the following fact. You have a function in the source. You want to measure how well this function, if a function works well in the source, is it also good in the target or not? So this row captures that phenomenon that translates the performance of function in the source to the target domain. So that's one definition. Uh, why this is important? We have derived also optimality minimax rate. So it shows that this row appears in the lower bound, meaning that it's a fundamental parameter. And the beauty of the theorem is that without knowing the row, without knowing the transfer distance, which is not estimable using finite samples, we can get the optimal rate. So meaning that we don't know rho, it could be large, it could be small, we don't know. But always we are getting the optimal possible achievable rate.
Hey, thanks for the talk. Yeah, so in this talk, you kind of like focused on outlier detection, which is like a binary classification. Like you mentioned, can this be extended to like heavily imbalanced multi-class classification?
Yeah, good question. So actually, we are also working on extending this framework to multi-class. I think I remember only one or two papers have been published regarding multi-class Neyman Pearson. We are not sure if we can trivially extend this problem to multi-class classification problem. Yeah, but still we are working how to extend this problem. Yeah, I don't know if you can trivially extend it to multi-class or not.
Thank you, Mohammad Reza, and thank you, Joe. At this point, you are welcome to join us for a light lunch. As always, Greg students, you get first dibs, so you can go to class. Thank you, everyone. And this was our last fall 2024 lecture in climate data science. So thank you all, and thank you online for joining us throughout the term. And we welcome you back. I think we kick off January 23rd. That's a Thursday. So yes, after the semester begins, January 23rd, I think is our first Thursday back. So we look forward to seeing you back then. Thank you, everyone.